So you'll remember that I begged you, implored, offered you my firstborn, whatever, to try to get you to watch the time value of money videos before we would have our class tonight. I did that because I'm not going to spend much time there at all. I'm going to just briefly hit a couple of concepts there, several of which we've already touched on. But that's where we kind of start tonight. If you've not done as I had asked you to do and are not nicely comfortable with time value of money metrics, you're going to need to watch those videos. They should present nothing new to you. These are concepts that I believe were displayed to you the first time in your 603 class. And you may have seen them if you've had 630 as well. But I'll hit on a couple of them. We're going to look briefly at those metrics. We're already starting to look at Excel with them and the equations. I'll briefly introduce the calculator to you. And then we'll look at some decision criteria that we think of as present value, net present value, internal rate of return, modified internal rate of return, payback, discounted payback, and the profit index. Then we'll look at a multi-columnar structure. We're going to look at some equational forms. And we'll look at some templates, and then we'll look at assignments that you've already looked at some of this. So I've got some dates here. These dates are not accurate. They're from a previous block, the spring block, so I apologize. So with that, let's begin a brief review of some of the time value of money metrics. None of this should be new to you, as I said earlier. So we've got two basic forms of a present value equation. It can be present value is equal to some amount in the future or a future value divided by 1 plus a discount rate. This R stands for discount rate. This is the basic discounting instruction. Some number that comes at us at a point in the future divided by 1 plus a discount rate to the power of whatever time passes between now and that future point in time. So this is a one economic exchange. We can use a summation term here where we have multiple exchanges in which beta stands for some benefit, time stands for, T stands for time, and R stands for a discount rate. And just as we talked about a few minutes ago or half an hour ago, whenever it was, a discount rate is just some rate that we use to quantify present value exchanges. It might be WACC if we're looking at something from the standpoint of the company. It might be an interest rate if we're looking at it from the standpoint of somebody that borrowed money in order to make an investment. So that might be a required return, might be a hurdle rate. But we got to use some rate. And if we're looking at more than one exchange, we're going to add all of those present values up. And we're going to get then the sum of the present values. And that's what's expressed here. So a simple example for this, being for the one-shot equation, would be if we put 100, and we know we got that $100, let's say if we receive that dollars 5 years from now, and if we discounted it at 6%, we would have 100 divided by 1 plus 0.06 or 1.06%. And we would take that number in the denominator to the 5th power because it's happening 5 years or 5 periods from now. And we know that $100 we get in 5 years would be equal to $74.72 today if it was being discounted at a rate of 6%. Well, it's as simple and as complex as all of that. And if we want to think about this in a little bit further, and we want to think that we've got some constant discount rate, and if we think about having some constant stream of payments, so they started at 100 and they keep going at 100, and we're discounting them, then summing all of those up at that constant stream, we've got this present value of this future income stream. And you'll notice that if I apply the annuity equation, the present value of an annuity equation, I get the same number. That's because an annuity equation is for a set period of time at a constant discount rate and a constant payment. So an annuity, a set period of time, a constant discount rate, and a constant stream of payments. So the payments don't change, the discount rate doesn't change, and time is specified. Well, that looks like the same exact number, of course, but what does this part of the equation look like to you? Does that look like any other equation that you've seen and worked with? What's it look like, Michael Schwartz? You're on mute, buddy.
Is it the bond calculation?
Looks like the first half of the bond calculation, where 100 is equal to C, 6% is equal to YTM, and 5 is equal to N. And in fact, the reason I put this next part here, but have a 0 in the numerator, is because this is the second half of the bond value equation, for which in the bond value, though, we know that 0 is replaced with 1,000. So this 0 would be the future value. So this is simply a singular equation. This is simply this equation for a value received at a future period of time. And this is the annuity equation, which is think of an annuity as being the interest we receive if we have invested in a bond. It's a set stream of payments for a specified period of time at a constant rate. It's an annuity plus a little bit of a kicker at the end when we get our money back. Michael Allen is very happy about this. I can tell because she's smiling so. Or something else is making her smile. My guess is maybe not the numbers, right, Michael? It's all good. Okay, so again, this is just a brief little review for you. And if you need more review, I've given you the videos. Watch the videos. This takes us now just along a slightly different route, where instead of having constant cash flows like we have here, constant cash flows, we have non-constant cash flows, where our betas now are changing. And it looks like they're changing at a constant interval of $25 per period. But that's, even though it's a constant interval, it's a non-constant percent change, because 25 is a different percentage of 100 than it is of 150 than it is of 175. Okay, so when we see this extended, the summation version, we can use it as a constant cash flow version. We can use it as a cash flow growing at a constant rate version. We can use it as a non-constant version. It's simply a summation, and you see how I put these numbers together, of course.
So just to clarify something you just said, Rick, so if you go back to the last slide for just one second. So I'm just trying to make sure I follow the difference in between those two, constant and non-constant. So I mean, I get the concept of, okay, you've got all those little, present value equations you're adding up over time, right? But sorry, clarify the difference on those.
You bet. So this line is virtually identical to both slides, okay? It begins to differ here, though, in that I'm using a constant benefit as my numerator. It's a constant cash flow. My benefit, my numerator, is always my cash flow. In this case, it's constant. Whereas here, it's not constant. It's changing.
Okay.
Okay. And in this case, I have it changing at a constant interval, but it's not changing at a constant rate, is it? A rate would be a percentage rate. So if I applied, say, a 5% growth rate to my cash flow, in the first year, it would be 100 times 1.05. And in the second year, it'd be 100 times 1.05 squared. Third, 100 times 1.05 cubed, etc. Well, that's not what this is doing either. So I'm showing you an example of a constant cash flow and a non-constant cash flow that's not at a constant rate. I could show you an example, as I do in the videos, of a non-constant cash flow that's at a constant rate of growth.
Right. And just to, so I think I follow you, just to frame it in like maybe a real world example. So you use the constant cash flow example as an annuity. What would be, like an example of some sort of investment or scenario of a non-constant cash flow?
You bet. So Matt, I would like you to invest in Rick Incorporated. And Rick Incorporated is projected to have a cash flow of $100 at the end of this coming year. And I believe that each year thereafter, that cash flow will grow by $25. And so we're going to have a cash flow coming out of Rick Incorporated for the next 5 years that will start at 100 and then go to 125, 150, 175, and then 200. So businesses invariably have non-constant cash flows. Now, in this case, I'm forecasting it, and which means I'm guessing, right? And the likelihood of my guesses being dead on accurate are pretty much, well, non-existent, but at least it's an educated guess based on my best forecasts. And next week, we're going to go ahead and look at forecasting, okay? It's hard to articulate what a non-constant cash flow at a constant rate of growth might look like because it's not an annuity. It's not a mortgage. It's not an investment plan that we know. It's not a business because businesses tend not to have their cash flows grow at a constant rate. Okay? We might forecast them at a constant rate, but they tend not to actually happen that way. But let's assume for a minute that your investment is a common stock. In, let's see, Bank of America Fork, common stock. It wasn't publicly traded. It was privately traded. And Bank of America Fork's common stock doesn't exist anymore. It was bought out by Alta Bank. But Bank of America Fork for decades, and I mean starting back in the early part of the 1900s, for many decades, it paid a dividend every calendar quarter, and that dividend increased at 2% every year come hell or high water. Through the Depression, it increased at 2%. Through the go-go 1990s, it increased at 2%. In the financial crisis, it increased at 2%. Now, you would agree that it did so artificially, but there was a commitment on the part of the decision makers in the company that their dividend was going to grow at a constant rate year in and year out forever. And it was a very healthy bank. That's kind of an odd example, but it's an example. Does that help?
Yeah, I think so.
Good. Well, if we have something where the cash flow is growing at a constant rate, and it's doing so in perpetuity, and the discount rate is consistent, we might see it here, and it's going to end up looking like the dividend yield or the Gordon growth model. If we change this to VAL, and we change this to cash flow, we now have a valuation model in the form of the Gordon growth model. Remember that the Gordon growth model is predicated upon a constant rate of growth of the cash flow. So if it's 2%, 5%, 110%, whatever it is, it does that year in, year out in perpetuity, a consistent discount rate, and the G that we see here is the growth rate of that cash flow. This is the Gordon growth model.
So would you just use that for forecasting though, since it, practically speaking, like you said before, businesses usually don't grow at a constant rate?
Well, that's a good question. And yes, I would use it, but I would only use it where my cash flows reach some normalized rate of growth. So let's say that Michael Allen and I put a business together, Allen Enterprises. And in this year, it's projected to have a $10 million positive cash flow. Because of next year's economic conditions, we expect that to be better. We won't have been dealing with COVID anything, hopefully, a year from now. We'll see. So we've got a growth rate there of maybe 15% over the next year, and a year after that, it's 9%. It goes up to 12%, and then afterwards, our crystal ball becomes very hazy. We can't forecast it, so we're going to give it some very nominal rate of growth, maybe the rate of growth of the economy at large. We're going to call that our long-run growth. We're going to call it 2.5%. Well, what we've just done is we've suggested that after some period of time where we could expressly forecast for each given year what our growth might be, we might beyond that have to consider that the rest of time, as we may know it, we have to forecast a rate of growth at some very nominal value, but we'll do it as our best guess. And we use the Gordon growth model as the second part of that.
I see. So basically, just because of the uncertainty of the further out you get in time, you know, to be, I don't know, I guess you could say conservative or more practical with what your estimations are, you use that model based because you have some actual current components like your actual cash flow and discount rate and whatnot that you can put into it to
Exactly
come
right.
up with some sort of actual plausible rate.
When I know that I don't know,
Right.
I get very protective, right? When I know I'm ignorant, I keep my mouth shut, as opposed to the times that I didn't know I was ignorant and should have kept my mouth shut, right? Okay, so we're thinking about the Gordon growth model. How many of you remember the functions that for the HP calculator to do basic time value of money work here? Just by raise of hands. Okay. So what I want to do with this and these, the parts of the slide here that are going to look at the calculator, I want to come back to these slides either at the end of the evening if we have time, and my guess is you're not going to want to, or Monday evening during a review after more of you might have reviewed these functions, because if you watched the videos I begged you to watch, you would have reviewed the functions and you would have remembered them, okay? So I don't want to spend this time now. We're going to come back at this when you've reviewed those and we all got a better basis to work from, because otherwise it's just going to kind of be a waste of time, okay? So let me kind of move through these real quickly, and if we have some better time, then we'll come back to them.